Thank you for joining the talk, and thank you for your interest in this topic. So I'm here to talk about Olympia. Olympia is our, out of order processor model, simulation model for an example RISC-V out of order processor. And this effort has been first introduced last year in the RISC-V Summit. And I'm here to talk about the state of that effort, what we have done in the last 1 year. And so it's important to note that it is not just my work. The SIG has been driving it, and there has been tremendous amount of contributions from many people who have taken interest in this work to devote their time apart from the day job, and we are grateful for their work, and I'm essentially talking about all of their work. Moving on, as a refresher, what is Olympia? Olympia is a open source cycle approximate performance model of an example superscalar out of order processor. It's a trace driven model. It runs instruction traces that are generated from the RISC-V binaries, and we also have the way how to generate the trace from the binaries. It is based upon this framework called SPARTA that has been around for quite some time, and it's a C++ based event-driven modeling framework that can be used to create microarchitectural simulations, run the simulation, gather performance data. And it has been driven, as I said, by the RISC-V Performance Modeling SIG. I am the chair of the SIG. Newt Lingard, who works in the Sci-Fi performance team, and he's the lead maintainer of SPARTA. He is the vice chair, and he provides a lot of technical support and guidance behind the SIG. And we have participation from industry and academia across multiple geographies. Our SIG meetings are almost always attended by people from Europe, Asia, North America, so it's truly global. Just a few statistics that I captured, like this may be a little stale. I captured a few weeks back. Let's say in past 2 weeks, there has been over 2,000 views of the GitHub repo, over 190 clones. There are about now, I think, 40 pull requests, about 12 contributors, active contributors. Moving past, so what was the state of the Olympia last year? So we intended to create a model, a C++ based model for a typical superscalar processor. It was an example processor. It was not representative of any, let's say, an industry processor that existed or would exist. Okay, just taking the common features of a typical superscalar. So that's an in-order fetch, in-order decode, and then in-order dispatch, then out-of-order execute, in-order retire. So we wanted to model that. And last year, our situation was this, that it fetched certain pre-decoded instruction from the instruction trace. It could dispatch to the correct execution unit, so it will dispatch the branch instruction to like the branch pipe. But we really did not have, for example, any dependency checking, so it did not have any register renaming. So you could, depending upon, even if we decrease the number of pipes, it almost acted as if there is no data dependency. And also the LSU was very simple. It's an in-order LSU. So that was the situation. But it's almost like the part of the front end was there, the dispatch worked, the raw was also working because we were doing in-order retirement, and so on. So that was last year. Now, since last year, what we have implemented. So one of the main things that we got done is rename. So rename was implemented so that we can actually model the data dependencies of our workload. So now we do fetch from the instruction trace. It is already pre-decoded because we use a format where the instructions are there. The decoding instructions are there using a decoder called Mavis, and then we do physical register renaming, and then we dispatch to the correct execution unit, do out of order execution, and then retire. We can also do now out of order, that's a typo, out of order issue for execution units, out of order load, store, execution with replace. Okay, so if we have cache misses, etc., we can do replace. We have non-blocking decache which can do hits and misses under miss, things like that, which are typical superscalar features. We can model those right now. Now, so the purpose of the model is to help us do performance analysis. So now the point is that if we use the Olympia, like if you go clone it from the repo and build it, what can you do with it? So this is an example of what you can do. So you can do reasonable performance analysis with it. So this is an example. So for example, we have in the model a certain inbuilt cores, small core, medium core, big core, where the number of the issue width is different, the execution units are different, and you can see that over these two traces, which is also there in the repo, that your performance, IPC varies. So you can do get this kind of data from the model today. And not just overall performance, you can also get like internal stall stats. There are many stats. This is just a very small sample. Here I'm showing the dispatch stall stats, and as you can see that as you go from small, medium, big core, the the performance gets, in this case, gets limited by the LSU. Similarly, if I did a study by changing the number of renamed registers, available physical renamed registers, and as you can see that for dry stone and core mark, as you increase renamed registers, your performance increases and then it tapers off. So these kind of studies are possible. And since I mentioned small, medium, big core, it's not that we can do analysis for only these cores. Since we're using the Sparta modeling framework, you can easily create your own code, okay? And for that, you do not even have to write C++ code. Like this is basically equivalent to editing an YAML file where you specify your number of pipes, okay, what kind of execution units, what's the size of the cache, and you can have your own core and do your performance studies using that core. So that's called like the core extension, Olympia core extension. Other improvements that we did, apart from improving the model, making it more featured, is we have created a Conda environment to help so that everyone can use that Conda environment to build Olympia. We have set up check-in regressions so that any change that goes to Olympia can go through that check. We have upgraded to the latest version of Sparta, which we thought is important. We have added unit testing framework that can be leveraged as we bring in new units like L2 cache, etc., which are being worked on right now. So we can do that, and we have really good community engagement. We have weekly SIG meetings, and actually it started with weekly, and actually right now there is some sort of sub-interest groups that have generated. Like we right now actually have like 3 SIG meetings that happen every week. On an average, we have good attendance. There is GitHub discussions that are going on whenever we want to model something, L2 cache, we put it on the GitHub discussion, and then people comment on it. We have one invited talk, and we also took advantage of the RISC-V mentorship program. So thank you RISC-V organizations for that, where we were able to recruit 3 mentees who worked and developed code for this, and they are still with us, continuing the development. So these are some of the things that is actively being worked on right now. The vector processing unit is being worked on, and if you go to the GitHub discussion, you'll see there are discussions going on about that. L2 cache, I cache, these are being worked on. There is some work going on in the branch prediction as well. Now, looking forward, what we want to do. So I already said that those are the areas which are actively where work is going on. Beyond that, we do want to do things like we want to model cache replacement policies, branch prediction policies through an API. So we want to create an API so that if you want to model your cache replacement policy or your own branch prediction policy, you can use that API and put it there without having to change too much. So that's the goal, and we are trying to achieve it. Add interconnect and memory subsystem. Extend Olympia so that it can be interfaced with external components, which may be modeled in System C. So if you have a System C component, can interface with Olympia. Scala, there has been some interest about interfacing Scala chisel-based designs as well. So it would be nice to support it. Improvements to the execution unit. So one improvement that we want to do is that currently the execution units are not pipelined. So this is one thing that we want to support, like where the execution units will be pipelined. Yeah, it's not too difficult to do, but it's one thing that needs to be done. So even though we have out of order LSU load store execution, we still have one pipeline. We want to develop multiple pipelines. Developing execution-driven model. Okay, so this is trace-driven. We want to integrate a functional model so that we can do an execution-driven model. So these are the things that we want to work on in future. And if you go to the repo, you would find a list of issues that you can see that if some of them interest you. Okay, so this is also an important slide. I want to mention a couple of people who have been working diligently on this. Newt, who is the vice chair and the lead maintainer of SPARTA. He has been, as I said, provides very important technical guidance behind this work. Aaron and Zain has developed the rename register, rename work. Suraj Vineet has been doing the LSU and Dcache modeling. Arya has helped us doing some tracing work and some branch prediction work. Kathleen has provided, from Sci5, has provided a lot of support throughout the SIG. And Brett and Peter has also contributed to this effort. So the topic of this talk is the state of Olympia. So this is sort of the takeaway points, that where do we stand right now? So last year what we intended, that we wanted to create a model which can be the starting point for anyone who is interested in doing performance analysis in RISC-V community. And I think we have gotten to that point. We are very close to that point. This is, anyone who is looking at interested in doing performance, they are looking at it as like their default starting point, and this is exactly where we want it to be. And it is getting a lot of critical mass in terms of contributions, model, features, and so on. But obviously there is more work to do, and so we have to keep the momentum going. And so here is where you can help if you are interested. You can help by attending our SIG meetings and providing feedback, suggestions, contributions. Even in the repo, there is opportunities to participate in the repo as well. If you would like to contribute code, develop, please, we welcome you. Please look at the issues, and maybe one of them would interest you. And in general, any feedback is welcome. And I think that's all I have. If you have any questions, I can take them now.
All right, I have a microphone here. Let's start with a round of applause first before we go to questions.
Okay.
We have enough time for one or two questions. This time, I don't have a question in mind myself personally, but surely somebody does. Right here behind me, of course, as always.
Good talk, Arup.
Thank you.
Right here.
Okay.
Hey. So how does your model compare and contrast with Gem5, which also supports RISC-V?
Okay. So, so when we started this effort, at that point, Gem5 wasn't an option. So we started this, and also we are not, trying to compete with Gem5. But I personally haven't used Gem5 a lot. But from the people who have used it, they have told us that it is, this is much more flexible in the sense that if you want to change your core, etc., you can easily do that without having to, write a lot of C++ code. So that is definitely one advantage we have over Gem5. Okay.
Okay. Excellent. Thank you for your question. Another question? Going once? Going twice? All right. Let's give Arup one last round of applause. Thank you, Arup.
Okay.
Nice job.
Thank you. Thank you.